Sir, start பண்ணலாம்.
Okay. Good morning, students. In the last class, we have started the 5th unit, classical theorems and the multiplicative functions. So I have discussed the Wilson theorem and the required lemma, and we solved few problems based on Wilson's theorem. So in the continuation, so we proved the lemma: a positive integer a is self-invertible modulo p if and only if a is congruent to plus or minus 1 mod p. Okay. And the statement of the Wilson theorem is, if p is a prime, then p minus 1 factorial is congruent to minus 1 mod p. And also we proved the sufficient condition: if n is a positive integer such that n minus 1 factorial is congruent to minus 1 mod n, then n is a prime. Then we have checked whether the given prime is self-invertible or not, and also we verified p minus 1 factorial is congruent to minus 1 mod p for p is equal to 5. And without using Wilson theorem, so we did one more verification, and we have found the remainder of 13 factorial when divided by 19 by using the Wilson theorem. And also we worked out to find the remainder of 97 factorial when divided by 101. So in the continuation, prove that 63 factorial is congruent to minus 1 under mod 71. Okay, which means, so it is like the previous problem, when 63 factorial is divided by 71, we can get the remainder minus 1. Okay, we can get the remainder minus 1. So which will be proved by using the Wilson's theorem. So you know the statement of Wilson theorem: p minus, if p is prime, then p minus 1 factorial is congruent to minus 1 mod p. Here the mod value is 71. So p value is 71. So 71 minus 1 factorial is congruent to minus 1 mod 71. So 71 minus 1, 70. So 70 factorial is congruent to minus 1 mod 71. But we want the remainder for 63 factorial is divided by 71. So 70 factorial is expanded, okay, in the descending order up to 63 factorial. Okay, so 70 into 69 into 68 into 67 into 66 into 65 into 64 into 63 factorial is congruent to minus 1 mod 71, which will be considered equation 1. Okay, so 70, we know 70 is congruent to minus 1 under mod 71. Okay, when 70 is dividing by 71, you can get the remainder minus 1. Then the next integer 69. So when 69 is dividing by 71, you can get the remainder minus 2. So 69 is congruent to minus 2 mod 71. So like 68 is congruent to minus 3 under mod 71. 67 is congruent to minus 4 under mod 71. And 66 is congruent to minus 5 mod 71. Then 65 is congruent to minus 6 under mod 71. 64 is congruent to minus 1 under mod 71. Okay, so you know how to write the remainder for 64. Actually, when 64 is dividing by 71, you can get the remainder minus 7. So this division algorithm is representing in the linear concurrence form. So linear concurrence form 64 is congruent to minus 7 mod 71. Okay. Now these congruent values will be substituted in the left hand side of equation 1. So 70 is congruent to minus 1, 69 is congruent to minus 2, into 68 is congruent to minus 3, 67 is congruent to minus 4, 66 is congruent to minus 5, and 65 is congruent to minus 6, and 64 is congruent to minus 7. Okay, under mod 71. Then you can get the product minus 1 into minus 2 into minus 3 into minus 4 into minus 5 into minus 6 into minus 1, that is minus 5040. 5040 under mod 71. So 5040 which is greater than 71, so which can be divided by, you can get the remainder minus 1. Already there is minus sign, so plus 1. So 70, from 70 up to 64, okay, whose product is congruent to plus 1 under mod 71, okay, which will be considered equation 2. This equation 2 will be substituted in equation 1, okay. In the equation 1, so look at the equation 1, the left hand side, the product 70 into 69 into 68 into up to 64, which is congruent to 1. So 1 into 63 factorial is congruent to minus 1 under mod 71. So 1 into 63 factorial is congruent to minus 1 mod 71, okay, which is proved. Okay, 63 factorial is congruent to minus 1 mod 71, which means when 63 factorial is dividing by the mod value 71, you can get the remainder minus 1. Okay, so which is the meaning of this linear congruence. Okay, so the next problem, so which is important one, if P is a prime, then prove that P minus 1 into P minus 2 into P minus 3 up to P minus K is congruent to minus 1 to the power K into K factorial mod P, where the K value, so the K value lies between 1 and P. Okay, so K value, the value of K is starting from 1, okay, up to P minus 1, okay, which is not equal to P. So K is less than P. So we know the Wilson theorem, statement of Wilson theorem, if P is prime, then P minus 1 factorial is congruent to minus 1 mod P. Okay, now which is easiest one? When P minus 1 is, so now, so P minus 1 factorial means P minus 1 into, P minus 1 factorial can be expressed as P minus 1 into P minus 2 into P minus 3 into up to 3 into 2 into 1. Okay, so P minus 1 is congruent to minus 1 mod P. So obviously you have known, since P minus 1 is dividing by P, you can get the remainder minus 1. Okay, next, then P minus 2. When P minus 2 is dividing by the mod value P, you can get the remainder minus 2. Therefore, P minus 2 is congruent to minus 2 mod P. So similarly, P minus 3 is congruent to minus 3 mod P. So up to the general form P minus K is congruent to minus K mod P. Okay. So now from P minus 1 to P minus K. Okay. So these primes will be multiplied together, correspondingly the right hand side, which is also multiplied. You can get P minus 1 into P minus 2 into P minus 3 into up to P minus K is congruent to minus 1 into minus 2 into minus 3 into up to minus K. Okay, under mod P. So here, how many minus sign we have? So 1, 2, 3 up to K times. Okay, so the number of minus sign is K times multiplied, therefore it can be written minus 1 to the power K. Okay, actually minus 1 into minus 2 can be represented minus 1 the whole square into 1 into 2. Suppose minus 1 into minus 2 into minus 3 means minus 1 the whole cube into 1, 2, 3. Here k times. So minus 1 to the power k into 1 into 3 into up to k. So in the next step, minus 1 to the power k. So we don't know whether k is even or odd. Okay. Suppose if k is even, then minus 1 power k becomes plus 1. If k is odd, minus 1 to the power k becomes minus 1. Here we don't know. So 1 into 2 into 3 into up to k, that is k factor. Okay. So p minus 1 into p minus 2 into p minus 3 up to p minus k, which is congruent to minus 1 to the power k into k factorial mod p. So which is proved. So this is one of the important results. And the next proof, if p is prime, sorry, odd prime, if p is odd prime, okay, so which is the key point. If p is odd prime, then prove that 1 square into 3 square into up to p minus 2 the whole square is congruent to minus 1 to the power p plus 1 divided by 2 mod p. Okay, so as usual, so all the results can be proved by the help of Wilson theorem. So by Wilson theorem, p minus 1 factorial is congruent to minus 1 mod p. Okay. So on the left hand side, p minus 1 factorial, which will be expressed p minus 1 into p minus 2 up to 1. Okay. So this expansion would be rearranged. So 1 into 3 into 4 into up to p minus 2 into p minus 1 is congruent to minus 1 mod p. So now we can, the product can be separated as odd and even integers. Odd and even integers. So collect only the odd integers 1, 3, 5, 7, like, okay. Therefore 1 into 3 into 5 into 7 into up to p minus 2 into, so even integers, product of even integers, that is 2 into 4 into 6 into 8 into up to p minus 1. Okay, since p is odd prime, p is odd prime. Okay, so p minus 1 should be even, p minus 2 should be odd. Okay, if p is prime, p is odd prime. Okay, suppose p is 7 means p minus 1, 7 minus 1, 6. So p is odd prime, then p minus 1 is even integer. So it's congruent to minus 1 mod p. So now, so 1 into 3 into up to p minus 2 into, now look at the product of even integers, 2 into 4 into 6 into 8. Okay, so now adding and subtracting p with each even integer, adding and subtracting p with each even integers. Okay, so the first even integer here 2. Okay, now adding and subtracting p. So 2 plus p minus p, 2 plus p minus p. So which will be rearranged. That is p minus of p minus 2, p minus of p minus 2. But you can simplify p minus of p minus 2. You can simplify now. Actually minus p. So when minus sign is taken inside the bracket, you can get minus p. Then minus into minus plus 2. So p cancel. I know. PP cancelator, there is 2. Only 2 is remaining. Okay, so each even integer 2, 4, 6, 8, 10. Okay, these even integers are adding and subtracting by p, and also it will be rearranged as p. So 2 can be written p minus of p minus 2. Okay, p minus of p minus 2. So 4 can be written p minus of p minus 4. Okay, then 6 can be written p minus of p minus 6. So like it. So it is considered equation 1. Now P minus of P minus 2. Okay. So P minus of P minus 2. Now you all know P minus 1 is congruent to minus 1 mod P. You have no P minus 1 is congruent to minus 1 mod P. Okay, P minus 2 is congruent to minus 2 mod P. P minus 3 is congruent to minus 3 mod P. P minus 1 is congruent to minus 1 mod P. P minus 2 is congruent to minus 2 mod P. Then P minus 3 is congruent to minus 3 mod P. So based on this, so P minus of P minus 2 is congruent to minus of P minus 2 mod P. Then P minus of P minus 4, which is congruent to minus of P minus 4 mod P. Then P minus of P minus 6 is congruent to minus of P minus 6 under mod P. So like P minus 5 is congruent to minus 5, P minus 3 is congruent to minus 3, P minus 1 is congruent to minus 1 mod P. So now it can be multiplied together. Okay, actually P minus of P minus 2 into P minus of P minus 4 into P minus of P minus 6 up to P minus 1. Okay, which will be multiplied together. Correspondingly, the right hand side of the congruence, which will be multiplied also under mod P. Okay, so you can get the number of congruences is P minus 1 by 2. The number of congruences is P minus 1 by 2. Okay. Since actually P minus 1 factor. So P minus 1 factor means 1 into 3 into up to P minus 1. Okay. So in the product, the number of integers is P minus 1. The number of integers is P minus 1. Am I correct? Actually 3 factorial. 3 factorial, for example, 3 factorial can be expanded as 3 into 2 into 1. So in this product, the number of integers are contributing is 3. Okay, suppose 4 factorial. 4 factorial means 4 into 3 into 2 into 1. Okay, so in this expression, 4 integers are contributing. Here, P minus 1 factorial. P minus 1 factorial means P minus 1 into P minus 2 into P minus 3 up to 3 into 2 into 1. So totally in the product, which are contributed by P minus 1 integers. Okay, so in the P minus 1 integers are equally separated by odd and even. Okay, 1 into 3 into 5 into up to P minus 1. Okay, then the remaining is 2 into 4 into up to P minus 1. So which is the even integer collection. So the number of odd integer collection is P minus 1 whole divided by 2. The number of even integer collection is P minus 1 whole divided by 2. Am I correct? Equally separated. Actually here P minus of P minus 2, P minus of P minus 4 up to P minus 1, which is the even number collection. Okay, so the number of even numbers is P minus 1 whole divided by 2. Therefore, the number of congruence is P minus 1 by 2. So now which will be multiplied together. So P minus of P minus 2 into P minus of P minus 4 up to P minus 1. Correspondingly, the right hand side is multiplied. So you can get so many minus signs. So the number of minus 1 is P minus 1 by 2 times. P minus 1 by 2 times. So when you are multiplying the right hand side of linear congruences, you can get minus 1 to the power P minus 1 by 2 into the remaining is P minus 2 into P minus 4 into P minus 6 into up to 5 into 3 into 1. Okay. So the left hand side of linear congruence is the product of even integers, which means 2 into 4 into 6 into 8 into up to P minus 1. Okay. So that integers was rearranged p minus of p minus 2 into p minus of p minus 4 into up to p minus 3 into p minus 4, p minus 1, which is congruent to minus 1 to the power p minus 1 whole divided by 2 into 1 into 3 into 5 into up to p minus 2 mod p. So this linear congruence is considered equation 2. Now this result will be applied in equation 1. So now substitute equation 2 in equation 1. Okay. So look at the left hand side of equation 1. 1 into 3 into up to p minus 2. So it is minus 1, that is product of even integers. The product of even integers which is congruent to minus 1 to the power p minus 2 into 1 into 3 into up to p minus 2, which is congruent to minus 1. Okay. The right hand side of equation 2 is substituted in the left hand side of equation 1. Okay. The left hand side means the product of even integers. The product of even integers 2 into 4 into up to p minus 1. Okay. Which is congruent to minus 1 to the power p minus 1 by 2 into p minus 2 into p minus 4 into 3 into 5 into 3 into 1. Okay. So now it's congruent to minus 1 mod p. So now here, so 1 into 1, 1 square, 3 into 3, 3 square, 5 into 5, 5 square, then p minus 2 into p minus 2, p minus 2 the whole square. Okay. So 1 into, so 1 square into 3 square into 5 square into p minus 2 up to p minus 2 the whole square, which can be written 1 into 3 into 5 into up to p minus 2 the whole square. Okay, the whole square. Now both sides multiplying by minus 1 to the power p minus 1 by 2. Now multiplying both sides minus 1 to the power p minus 1 by 2. Okay, so in the left side minus 1 p minus 1 by 2 again is multiplied with minus 1 to the power p minus 1 by 2, which means minus 1 p minus 1 by 2 the whole square, which becomes plus 1. In the right side already there is minus 1, so minus 1 into minus 1 to the power p minus 1 by 2. Okay, so the basic rule of algebra is when multiplying the two numbers, at the time the power is, when you multiplying the two integers, when the base is equal, then power will be added. Okay, here the power is p minus 1 by 2 plus 1. So p minus 1 by 2 plus 1. So it will be simplified. You can get p plus 1 by 2. Okay, by taking 2 as the LCM, you can get p minus 1 plus 2 whole divided by 2. That is p plus 1 by 2. So 1 into 3 into up to p minus 2 the whole square is congruent to minus 1 to the power p plus 1 whole divided by 2 mod p. By any doubt in this problem? But kindly go through this problem. So do you have any clarification? You can ask me now. Okay. So shall I move on the next problem? If p is a prime, then show that 2 times of p minus 3 factorial plus 1 is a multiple of p. Okay. So this result also be proved by using Wilson theorem. So statement of Wilson theorem, p minus 1 factorial is congruent to minus 1 mod p. Okay. The right hand side, there is a minus 1 which becomes on the left hand side. So p minus 1 factorial plus 1 is congruent to 0 mod p. Okay. the theorem is rearranged. The minus 1, the left hand side minus 1, which becomes on the actually right hand side of linear congruence is minus 1, which becomes on the left hand side. So minus 1 becomes plus 1. So p minus 1 factorial plus 1 is congruent to 0 mod p. So where p is prime. Then p minus 1 factorial, which will be expanded p minus 1 into p minus 2 into p minus 3 factorial. Okay. So stop at p minus 3 factorial. Since in this problem we have to prove 2 into minus 3 factorial plus 1 is a multiple of p. So that's why p minus 1 factorial was expanded up to p minus 3 factorial. Okay, now p minus 1 into p minus 2. The product of p minus 1 into p minus 2 is p square minus 3p plus 2. So it is into p minus 3 factorial is congruent to 0 mod p. So now p square minus 3p plus 2. So in the quadratic expression, p square minus 3p, which will be multiplied with p minus 3 factorial. Okay, p square, the first two term of the quadratic expression in p, that is p square minus 3p, will be multiplied with p minus 3 factorial. Then the last one, integer, plus 2 into p minus 3 factorial. Okay, is congruent to 0 mod p. So now, so 1 plus p square minus 3p. From p square minus 3p, p can be taken out as a common. So p into p minus 3 into p minus 3 factorial plus 2 times of p minus 3 factorial is congruent to 0 mod p. Okay. So keep 1 plus 2 into p minus 3 factorial on the left hand side. Okay. The remaining will be taken out. The right side. Minus, so 1 plus 2 into p minus 3 factorial, okay, which is kept on the left hand side. The remaining term, p into p minus 3 into p minus 3 factorial, okay, which is taken on the right hand side. You can get minus p into p minus 3 into p minus 3 factorial, actually, which is congruent to 0, okay. Actually, p into p minus 3 into p minus 3 factorial, the product can be divided by p. At the time, you can get the remainder 0. Therefore, 1 plus 2 into p minus 3 factorial, which is multiple of 3. Okay, which is a multiple of 3. The multiple of p. That's why you can get the remainder 0. That's why you can get the remainder 0. So we have proved 1 plus 2 into p minus 3 factorial is a multiple of p. Okay. Are you clear now? Actually, by the last step, 1 plus p into p minus 3 into p minus 3 factorial plus 2 times of p minus 3 factorial. So keep 1 plus 2 into p minus 3 factorial on the left hand side. The remaining p into p minus 3 into p minus 3 factorial. Okay. So which is multiple of So when you look at the expression, so p into p minus 3 into p minus 3, which is multiple of 3 at the time, which will be divided by p, you can get the remainder 0. So obviously, we can conclude that 1 plus 2 into p minus 3 factorial is a multiple of p. So the next topic, Fermat's little theorem. Okay. So before discussing about the theorem and the proof, we have to see the lemma. So the lemma will be used for proving the Fermat's little theorem. Okay. So before entering to prove the Fermat's little theorem, we'll see the lemma. Let p be a prime and a be any integer. such that P does not divide A. Okay, P does not divide A, which means P does not divide A means P does not divide A means P is not equal to 1, and also P is not equal to, sorry, A is not equal to 1, and also A is not equal to P. Then the least residue of the integers A, 2A, 3A up to P minus 1 into A modulo P are a permutation of the integers 1, 2, 3, etc. P minus 1. Okay. So this is the lemma needed to prove the Fermat's little theorem. Okay. Again, I will repeat the statement of the lemma. Let P be a prime and A be any integer such that P does not divide A, then the least residues of the integers A, 2A, 3A, 4A up to P minus 1 into A modulo P or a permutation of the integers 1, 2, 3 up to P minus 1. Okay. So this proof of the lemma is consisting two parts. So in the first part, we have to prove I into A. Okay, I into A is not congruent to 0 mod P. Here I takes the values between 1 and P minus 1. Okay. So then we have to show that the least residue of IA and JA modulo P are distinct. Okay. If I is equal to J, then I and J takes the values between 1 and P minus 1. Okay. So both can be proved in the first part. IA is not congruent to 0 mod P, and also the least residues IA and JA are distinct under mod P. Okay. For proving equation 1, okay, so it can be proved by method of contradiction. Suppose IA, so we have assumed IA is congruent to 0 mod P. IA. Suppose we have assumed IA is congruent to 0 mod P. So which means P divides IA. IA is congruent to 0 mod P means when IA is dividing by P, you can get the remainder 0. Which means IA is divisible by P. That's why we are able to write P divides IA. P divides IA means P divides IA means P divides C. P divides I and also or P divides C. But initially but actually P does not divide. Okay, actually P does not divide. So P does not divide. Okay, so this is impossible since the I value is always less than P. The I value is always less than P. That's why P does not divide I. Okay, so therefore IA is not congruent to 0 mod P. So IA is not congruent to 0 mod P. Okay, then so now the least residues are distinct. Now we are going to prove the least residues are to be distinct. Suppose IA and JA, so both are congruent. IA is congruent to JA mod P. We know the I and J values are lying between 1 and P minus 1. Okay, and also the GCD between A and P. The GCD between A and P is 1. The GCD between A and P is 1. Therefore, IA congruent to JA mod P can be written I is congruent to J mod P since the GCD between P and A is 1. So that's why I have written I is congruent to J mod P. So where I and j as least residues modulo p, I and j as least residues modulo p, then the only possible is I is equal to j. Okay, the only possible is I is equal to j. So equation 2 is also proved. So in other words, so it can be described in another words, no two least residues of a comma to a comma b. Okay, so no two least residues of a comma to a comma 3a up to p minus 1 into a are congruent to modulo p. Okay, so we have proved the lemma. We have proved the lemma. So now, so the main theorem, Fermat's little theorem. Sometimes the statement of the Fermat's little theorem will be asked in the under part E. Okay, suppose they may ask the proof which is under part B question. Let P be a prime and A be any integer such that P does not divide A, then A power P minus 1 is congruent to 1 mod P. Okay. Again, I will repeat the statement of the Fermat's little theorem. Let P be a prime and A be any integer such that P does not divide, then A power P minus 1 is congruent to 1 mod P. So just now we proved the lemma. So in this lemma, the statement of the lemma is the least residues of the integers a comma 2, a comma 3a up to p minus 1 into a are the same as the integers 1 comma 2 comma 3 up to p minus 1. Okay, in some order. Okay, you can get the any order. The products are congruent to modulo p. Okay, which means a into 2a into 3a into up to p minus 1 into a, which is congruent to 1 into 3 into 3 4 into up to p minus 1 mod. In the left side a into a square. Suppose a is multiplied 2 times means a square. Suppose a is multiplied 3 times means a cube. Here the left side a is multiplied p minus 1 times. So this product can be written a power p minus 1 into 1 into 2 into 3 into up to p minus 1, that is p minus 1 factorial. Okay, so a power p into p minus 1 factorial is congruent to, in the right side, 1 into 3 into up to p minus 1, that is p minus 1 factorial mod. So both sides p minus 1, so p minus 1 factorial, both sides. So simply p minus 1 factorial is cancelled on both sides of the linear consequence. You can get a power p is congruent to 1 mod. A power p is congruent to 1 mod. Okay. So we have proved the Fermat's little theorem. Okay. Let p be a prime and a be any integer such that p does not divide. The condition is p does not divide. At the time, we can write a power p minus 1 is congruent to 1 mod p. So we'll see the corollaries. If p and q are distinct primes, if p and q are distinct primes, then p power q minus 1 plus q power p minus 1 is congruent to 1 mod pq. Okay, mod pq. Actually, p into q means the LCM of p and q. The LCM of p and q. That is p into q. So which can be proved by using Fermat's little theorem. You know the statement of Fermat's little theorem. A power p minus 1 is congruent to 1 mod p. Okay. So now, since q is a prime, okay, first initially I am taking q as a prime. So since Q is a prime, Q does not divide P. Q does not divide P. Then we can write P power Q minus 1 is congruent to 1 mod Q. Okay. If Q does not divide P, we can write P power Q minus 1 is congruent to 1 mod Q. Okay. This is equation 1, which was written by using Fermat's little theorem. Okay. So we know that Q is congruent to 0 mod Q. Obviously, correct? When Q is dividing by Q, you can get the remainder 0. So the linear congruence will be Q is congruent to 0 mod Q. So taking the power P minus 1, both are taking the power P minus 1. So Q power P minus 1 is congruent to 0 mod Q. Okay. So now adding equation 1 and 2. Now adding equation 1 and 2. P power Q minus 1 plus Q power P minus 1 is congruent to 1 plus 0 mod Q. That is 1 mod Q. Okay. So equation 3 is proved. Okay. Here I have assumed Q is a prime and P is any integer. Okay. Now the reverse part. Now we are going to assume P is a prime and Q is any integer. Okay. Now P is also a prime and P does not Q. So P does not divide Q. Then we can write Q power P minus 1 is congruent to 1 mod Q. This is equation number 4. So which was written by the help of Fermat's little theorem. Okay. In this part, we have assumed P as a prime. Okay. So obviously we can write P is congruent to 0 mod P. Okay. When P is dividing by P, you can get the remainder 0. So obviously we can write P is congruent to 0 mod P. Okay. Now taking the power on both sides, Q minus 1. So P power Q minus 1 is congruent to 0. 0 power anything 0 mod P. That is equation 5. Now adding equation 4 and 5, you can get Q power P minus 1 plus P power Q minus 1 is congruent to 1 mod P. Already you have proved equation 3. So from equation 3 and equation 6, so both can be combined. So P power Q minus 1 plus Q power P minus 1 is congruent to 1 mod. Actually, equation 3. In the equation 3, where mod value is Q. In the equation 6, where mod value is P. But the left hand side, the combination is same. Therefore, we can take here the mod value will be the LCM between P and Q. Okay, the LCM between P and Q is P into Q, since P and Q are distinct primes. Okay, so for the distinct primes, the LCM for the two distinct prime P and Q is P into Q. Therefore, mod PQ. The left side P power Q minus 1 plus Q power P minus 1 is congruent to 1 mod PQ. So in the 50 units, so far we have discussed Wilson theorem and the problems based on Wilson theorem. And so in the class, we have seen the lemma and the Fermat's little theorem, and we have discussed one corollary. And the second corollary is, if P and Q are distinct prime, then prove that P power Q.
Hello.
Sir?
Time முடிஞ்சிருச்சு sir.
Okay. Okay, students. So we'll discuss in the next class. Okay. Thank you, students.